These are Ncert exercise questions from the lesson Electrochemistry. Arrange the following metals in the order in which they displace each other from their salts. As per the activity series, the metal with the lowest reduction potential is the most reactive metal. Here, among the given metal, magnesium is the most reactive metal because it has the lowest reduction potential, and magnesium can displace aluminum, zinc, iron and copper, and copper is the least reactive metal. Given the standard electrode potentials of potassium, silver, mercury, magnesium and chromium, arrange these metals in the increasing order of reducing power. Reducing power means tendency for reducing agent will undergo oxidation. So which has the greatest tendency for oxidation. The metal with the lowest reduction potential has the highest tendency for oxidation. Here the metal with the lowest reduction potential value is for potassium and the highest is for silver. So we can say silver has the least reducing power and potassium has the highest reducing power. So lower the reduction potential, more easily it will be oxidized. Silver less than, mercury less than, chromium less than, magnesium less than potassium. Depict the galvanic cell in which the reaction Zn plus 2Ag plus gives Zn plus 2Ag takes place. Further show which of the electrode is negatively charged, the carriers of current in the cell, individual reaction at each electrode. Which of the electrode is negatively charged? That is, zinc electrode is the negatively charged electrode because zinc is undergoing oxidation to Zn2+. The carriers of current in the cell. In the external circuit, electrons are the carriers of current, but in solution, ions are the carriers of current. The individual reaction at each electrode. Here we can see zinc is oxidized to Zn2+. So for balancing, we can add 2 electrons in the right hand side. That is the oxidation half reaction. And 2Ag plus 2 electrons gives 2Ag. That is the reduction half reaction. Also, it is asked depict the galvanic cell. So we can represent the galvanic cell. Zinc is oxidized to Zn2+. That is the oxidation half reaction. Then salt bridge Ag plus slash Ag. This is the representation of galvanic cell. Calculate the standard cell potentials of the galvanic cell in which the following reaction takes place. Also calculate delta G naught and equilibrium constant for the reaction. So first let us calculate the standard cell potential, that is E naught cell. E naught cell is equal to E naught cathode minus E naught anode. Here the cathode is cadmium because we can see cadmium is undergoing reduction and also its reduction potential is higher than the potential of chromium. So let us take the difference 0.40 minus 0.74. When we take the difference, we will get 0.34 volt. Now let us calculate the standard Gibbs energy delta G naught. Delta G naught is equal to minus NF E naught cell. Now let us calculate the number of moles of electrons involved. 2Cr is undergoing oxidation to 2Cr3+. So here to balance the charge we can add 6 electrons. Similarly 3Cd2 plus 6 electrons gives 3Cd. So here the number of moles of electron involved is 6. So N equal to 6 minus 6 into Faraday's constant, we can take it as 96,500 coulomb per mole, and E naught cell is equal to 0.34. So when we multiply, we will get minus 196860 coulomb volt, that is joule, that much joule per mole. Now let us calculate the equilibrium constant. Delta G naught is equal to minus 2.303 RT log K or RT log Kc. So here K is the equilibrium constant. So let us substitute the values. Minus 2.303 into R value 8.314, temperature 298 Kelvin, 298 log K. So log K is equal to, let us cancel negative sign from both sides. So 196860 divided by 2.303 into 8.314 into 298. So when we simplify, we will get 34.5014. Now K is equal to anti-log of 34.5014. So anti equal to 3.192 into characteristic part is 34, so 10 raised to 34. Now let us do the B part. Here also we can calculate E naught cell. E naught cell is equal to E naught cathode minus anode. Here silver is undergoing reduction and iron is undergoing oxidation. Let us compare both reduction potential. Reduction potential is higher for silver. So silver is undergoing reduction and iron is undergoing oxidation. So cathode minus anode. So 0.80 minus 0.77 volt. So when we take the difference, we will get 0.03 volt. Now delta G naught is equal to minus NF E naught cell. Here let us calculate the number of moles of electrons involved. Ag plus electrons gives Ag, that is the reduction half reaction, and Fe2 plus gives Fe3 plus 1 electron. So here the number of moles of electron involved is 1. So we can write N equal to 1 minus 1. F is Faraday's constant. We can take it as 96,500 coulomb per mole. And E naught cell is equal to 0.03 volt. So when we simplify, we will get minus 2895 joule per mole. Coulomb volt, that is joule per mole. Now let us calculate the equilibrium constant. Delta G naught is equal to minus 2.303 RT log K. So let us substitute the values. Minus 2895 is equal to minus 2.303 into 8.314. Temperature is 298 Kelvin. 298 into log K. So let's cancel negative from both sides. So log K is equal to 2895 divided by 2.303 into 8.314 into 298. So when we simplify, we will get 0.5074. Then K is equal to anti-log of 0.5074. So that will be equal to 3.22. The Nernst equation and EMF of the following cells Mg/Mg2 plus Cu2 plus /Cu. Here magnesium is undergoing oxidation. So we can write the oxidation half equation. Mg gives Mg2 plus 2 electrons. That's the oxidation half reaction. Similarly, reduction half reaction Cu2 plus 2 electrons gives Cu. This is the reduction half reaction. Now when we add this two, we will get Mg plus Cu2 plus gives Mg2 plus Cu. Now Let us calculate E naught cell. E naught cell is equal to E naught cathode minus anode. So E naught cathode is here copper. Its potential is 0.34 minus potential of magnesium electrode, that is you will get from the activity series. It is minus 2.37. So when we simplify, we will get 2.71 volt. Now let us write the Nernst equation, that is E cell is equal to E naught cell minus 2.303 RT by NF, that is the general equation, 2.303 RT by NF log concentration of product. Only we will consider the ions. So Mg2 plus divided by concentration of Cu2 plus, because concentration of copper solid and magnesium solid we can take it as unity. So 2.303 RT by F, 2.303 into 8.314 into 298 divided by 96,487. When we simplify these values, we will get 0.059. So let us directly substitute that value in the equation, minus 0.059 divided by N. The number of moles of electron involved is 2. So we can write log concentration of Mg2 plus given in the equation as 0.001 divided by concentration of Cu2 plus is given as 0.0001. So when we simplify, we will get it as 10 times. Then 2.71 minus 0.059 by 2 means 0.0295. Log 10 is 1. So 2.71 minus 0.0295. We will get 2.6805. So we can write it as this much volt. Now we got E cell as 2.68 volt. Next, the second question. Fe is undergoing oxidation to Fe2 plus and H plus is undergoing reduction. So we can write the oxidation half equation. Fe gives Fe2 plus plus 2 electrons, and the reduction half equation as 2H plus plus 2 electrons gives H2. So here the number of moles of electrons involved, N equal to 2. Now let us calculate E naught cell, that is E naught cathode minus E naught anode. So reduction potential of hydrogen electrode, hydrogen is the cathode and iron is the anode. So reduction potential of cathode is equal to 0.0 volt. Hydrogen is, its potential is 0 volt, and the potential of iron is minus 0.44. So we will get plus 0.44 volt. Now E cell is equal to, let us go back to Nernst equation. E cell is equal to E naught cell minus 0.059 by N, that is equal to 2 log concentration of product. Product side we have only Fe2 plus, concentration of Fe2 plus divided by, here we can write the overall equation as Fe plus 2H plus gives Fe2 plus plus H2. So divided by concentration of H plus, and coefficient of H plus is 2. That coefficient should be raised as power. Now we have calculated E naught cell, that is equal to 0.44 volt minus 0.059 by 2 log concentration of Fe2 plus is given as 0.001 and concentration of H plus is given as 1 molar. So 1 square is equal to 1. Then that is equal to 0.44 minus 0.0295 log. Here we will get 0.001. We can write it as 1 into 10 raised to minus 3. That is log 10 raised to minus 3. Log 10 raised to minus 3 is equal to minus 3. So 0.44 minus 0.0295 into minus 3. So that is equal to 0.44 plus, when we multiply we will get 0.0885. So that will be equal to 0.0885 and 0.44. You will get 0.5285. So we can take it as 0.53. That is the E cell. Now the third question. Sn is undergoing oxidation and H plus is getting reduced. So Sn gives Sn2 plus 2 electron. That is the oxidation half reaction. It's the anode. And 2H plus 2 electrons gives H2. That is the reduction half reaction. So let us write the overall equation. Sn plus 2H plus gives Sn2 plus H2. Here N equal to 2. And the potential of tin electrode is minus 0.14 volt. Now E0 cell is equal to E0 cathode minus anode. Cathode is hydrogen, its potential is 0 volt. So minus 0.14 volt. That will be equal to plus 1.14 volt. Now Nernst equation E cell is equal to E0 cell minus 0.059 by N is equal to 2 log concentration of Sn2 plus by concentration of H plus. The coefficient will be raised as power. So that is equal to 0.14 minus 0.0295 log concentration of Sn2 plus is 0.050 by 0.020 the whole raised to 2. So that is equal to 0.14 minus 0.0295 log 50 into 10 raised to minus 3 by 20 into 10 raised to minus 3 the whole square. So I can write 20 into 10 raised to minus 3 the whole square. So that will be equal to 0.14 minus 0.0295 log 50 into 10 raised to minus 3 divided by 20 into 20 into 10 raised to minus 6. So I can cancel minus 3 from both sides and we can take minus 6 to the numerator. So it will be plus 3 and 50 into 10 raised to plus 3. So that is equal to 0.0295 log 50 into 10 raised to 3 divided by 20 into 20. So that will be 5000 divided by 40. 0.0295 log 5 by 4. So log 125. Then that is equal to 0.14 minus 0.0295 into log 125 will be 2.0969. So when we simplify, we will get 0.078. 0.078 volt. Next question, PT/Br2 / Br minus H plus / H2. Here both are written in terms of reduction. So let us write the oxidation half equation. Br minus to Br2. 2 Br minus gives Br2 plus 2 electron. That's the anode reaction. That's the oxidation half reaction. And 2H plus 2 electrons gives H2. That is the reduction half reaction. Now let us write the overall equation. 2Br minus plus 2H plus gives Br2 plus H2. Now E0 cell is equal to E0 cathode minus E0 anode, that is 0 minus potential of bromine is 1.08. So our E0 value is negative 1.08 volt. Now let us go back to the Ncert equation. E cell is equal to E0 cell, that is minus 1.08 minus 0.59 by the number of moles of electron involved is 2. So log concentration of product side we don't have any ions. Bromine is in liquid state and hydrogen is in gaseous state. And so let us write 1 divided by concentration of Br minus raised to 2 into concentration of H plus raised to 2. So that will be equal to minus 1.08 minus 0.0295 into log 1 by 0.01 means 1 into 10 raised to minus 2. So 10 raised to minus 2 the whole square into, and concentration of H plus is 0.03. So that is also 0.03 the whole square. That is 3 into 10 raised to minus 3, 0.03 the whole square. That is 3 into 10 raised to minus 2 the whole square. So that is equal to minus 1.08 minus 0.0295 log 10 raised to minus 2 the whole square is 10 raised to minus 4. So that will go to the numerator as plus 4. And 3 into 10 raised to minus 2 the whole square, that also 9 into 10 raised to minus 4, that will go to the numerator as plus 4. So log 10 raised to 8 by 9 minus 1.08 minus 0.0295 log 10 raised to 8 by 9. So that is equal to, when we simplify, we will get minus 1.08 minus 0.0295 log 10 raised to 8 is 8, and log 9 we can subtract from that. So we will get log 10 raised to 8 by 9, we will get it as 7.0457. That is equal to minus 1.08. The second quantity is also negative quantity. So the overall value is negative. So this reaction is not feasible. So if we have to get positive E cell value, we have to reverse it. In cells widely used in watches and other devices, the following reaction takes place. Zn plus Ag2O plus H2O gives Zn2 plus 2Ag plus 2OH minus Determine delta G naught and E naught for the reaction. So E naught cell is equal to E naught cathode minus E naught anode. Here the cathode is silver electrode. It is undergoing reduction and the reduction potential of silver is 0.80 volt. And reduction potential of zinc electrode is minus 0.76 volt. So E naught cell is equal to E naught cathode minus E naught anode, that is equal to 0.80 minus 0.76, that is equal to 1.56 volt. Now delta G naught is equal to minus NF E naught cell. Now let's calculate the number of moles involved. In Ag2O, 2 Ag plus 2 silver ions are there, plus 2 electrons will give you 2 Ag. And zinc is undergoing oxidation, so Zn gives Zn2 plus 2 electrons. So the number of moles of electron involved in the redox reaction is 2 minus 2 into Faraday's constant 96,487. So we can take it as 96,500 into E naught cell is equal to 1.56 volt. So that is equal to, when you multiply, we will get 301080 joule per mole. That is 3.01 into 10 raised to 5 joule per mole. Conductivity of 0.20 molar solution of KCl at 298 Kelvin is 0.0248 Siemens centimeter inverse. Calculate its molar conductivity. Here concentration is given as 0.20 molar, that means 0.20 moles per liter. And conductivity is 0.0248 Siemens centimeter inverse. So molar conductivity is equal to conductivity by C. That is, here for converting liter we can multiply by using 1000. So by liter means 1 liter is 1000 cubic centimeter. So if the concentration is given in mole per liter and conductivity is given in Siemens centimeter inverse, we have to multiply by using 1000. So 0.0248 into 1000 divided by 0.20. When we simplify, we will get 124 Siemens centimeter square mole raised to minus 1. Conductivity cells containing 0.001 molar KCl solution at 298 Kelvin is 1500 ohm. What is the cell constant if the conductivity of 0.001 molar KCl solution at 298 Kelvin is 0.146 into 10 raised to minus 3 Siemens centimeter inverse? So first we have to calculate cell constant. Cell constant is equal to conductivity into resistance. Here conductivity is given as 0.146 into 10 raised to minus 3 Siemens centimeter inverse, and resistance is given as 1500 ohm. So cell constant is equal to 0.146 into 10 raised to minus 3 into 1500. So when we simplify, we will get 0.219 centimeter inverse. Conductivity of 0.00241 molar acetic acid is 7.896 into 10 raised to 5 Siemens centimeter inverse. Conductivity is given. Calculate its molar conductivity. If lambda m0, that's the limiting molar conductivity for acetic acid, is 390.5 Siemens centimeter square mole raised to minus 1. What is its dissociation constant? Here we have to calculate molar conductivity and dissociation constant. Here concentration is given, that is 0.00241 molar, and conductivity is given as 7.896 into 10 raised to minus 5 Siemens centimeter inverse. Then molar conductivity lambda m is equal to K into conductivity into 1000 by C. Here we are using 1000 because the concentration unit is molar, that is mole per liter, but the conductivity unit is Siemens centimeter inverse. So we are converting this liter into centimeter cube. 1 liter is equal to 1000 cubic centimeter. K into 1000 by C. 7.896 into 10 raised to minus 5 into 1000 by C. 0.00241. So when we simplify, we will get 32.76 Siemens centimeter square mole raised to minus 1. Now let us calculate dissociation constant. Dissociation constant means K, that is equal to C alpha square by 1 minus alpha. So first let us find out the degree of dissociation alpha. Alpha is equal to lambda m by lambda m0. Lambda m0 is the limiting molar conductivity. Molar conductivity is 32.76 and the limiting molar conductivity is given as 390.5. 390.5. So when we simplify, we will get 0.0838. This is the degree of dissociation. Now K is equal to C alpha square by 1 minus alpha. Here 0.00241 into 0.0838 the whole square by 1 minus 0.0838. So when we simplify this, we will get 1.86 into 10 raised to minus 5.